So before the break, we defined ideals, gave some examples, then talked about some operations on ideals, how to get new ideals from older ones. You can intersect them, add them, multiply them, etc. So the next main thing would be to do the quotient construction for rings and do the isomorphism theorems, give some examples. Now before that, I want to talk about this theorem we had in group theory, which was sort of the master theorem to prove all the isomorphism theorems. I'll remind you, so we suppose we have three rings, A, how do I want to write them, B and C, and we are given two ring homomorphisms, a ring homomorphism from A to B called F, and a ring homomorphism from A to C called G. And the question that this theorem wants to address is, when is there a ring homomorphism from B to C called H, such that applying F and then applying H amounts to applying G. So going down right and then up right amounts to going straight right. Okay, and if A, B, C were groups and these were group homomorphisms, we had a theorem which said that if the kernel of F is in the kernel of G, the kernel of F is a subset of kernel of G, then, and a little more F has to be onto, then there exists such an H and it's unique. And then there was some more refinement. And exactly the same thing is true for ring homomorphisms. Almost the same proof goes through. So we'll go through this quickly. I wrote down the statement here. Let's see. Let's put it up. Let me go over this with you. So it says, let A, B, C be three rings. Let F from A to B and G from A to C be ring homomorphisms. Part 2 is the main part. Part 1 tells you what the necessary condition has to be. So suppose part 1 says, if there exists a ring homomorphism H from B to C such that H circle F is G, then you must have this condition that the kernel of F has to be a subset of kernel of G. Right? So that is a necessary condition. Now part 2 says, suppose that condition is satisfied and further that F is onto. If F is onto, we denote that with a double arrow, if you remember. Then here, part A of 2, there exists a unique ring homomorphism H from B to C such that applying F then applying H amounts to applying G. Okay. And then part B, C, D, so this is the crux of the business, part A of 2. And then B, C, D are sort of refinements. If G is onto, then H is onto. If the kernels are actually equal, then H is 1 to 1. And part D is just pulling together B and C. So if G is onto and the kernels are actually equal, then H is 1 to 1 and onto. So it's a bijection. From part A, I already know it's a ring homomorphism, so it has to be a ring isomorphism. The proof is exactly like the proof in the group theory case. In fact, the situation is better because most of it I can get just by quoting that group theory theorem. So I'll just maybe write a plan of proof or something. Note A, B, C are abelian groups in particular. Under the plus operation. And F and G are group homomorphisms in particular. being a ring homomorphism is more than being a group homomorphism. So F and G are in particular group homomorphisms. And the kernel means exactly the same thing, whether you think of these as abelian groups or you think of these as rings. So I can literally quote that group theory theorem, and what do I get? I get the existence and uniqueness of I get part 1 first of all, and then in part 2 I do get that there exists a group homomorphism H from B to C, and a unique one, such that H circle F is G. So that's a part of proof of 2, because 1 is straightforward. So from the similar theorem in group theory, we get the existence of a group homomorphism H from B to C such that F followed by H is G, and its uniqueness such an H, and also part B, C, D. So what is left? What is left is to show that H is a ring homomorphism, that this H not just preserves addition, but it preserves multiplication. And to do that, you'll need to recall the construction of H. So let me just remind you the construction of H in this picture. So to construct this H, you start with a B in B, and you want to make some element in C. There's no direct way to go, so what you do is you choose a in A which maps to B when you apply F. Why can I choose such a? Because F is onto. That's part of my assumption in part 2, right here. And then you choose this A and apply G to it. Now you get a thing in C. And you would like to define H of B to be this G of A. But of course, if I give you this B, this A is not uniquely determined. I could choose a A and you could choose a different A prime, both of which map to B. Then we better make sure that these two guys go to the same place when I apply G to them. And that's the crux of the verification that one needs to do. So suppose in A such that F of A is F of A prime. So F of A minus A prime is 0. That means what? That means that the difference is in the kernel of F. And exactly here you see the condition on the kernels. The key condition comes into play. If this difference is in the kernel of F, then it's also in the kernel of G, because the kernel of F is in the kernel of G. So G of A minus A prime is 0, and that implies G of A minus G of A prime is 0. So G of A is G of A prime. So indeed, if we pick different elements A and A prime mapping to B, then they would go to the same place as when we apply G to them. Our condition on the kernel ensures that. So now we can define, let's say, definition of H down here. Given B in B, choose A in A such that F of A is B, and define H of little b to be G of this A. Why can I choose such a little a? Because F is onto. Is this unique? No, But if you choose different A's, it does not matter. You'll still get the same G of A. That's what we verified up here. So this is well defined. So and then one verifies that H is actually a ring homomorphism. So exercise verify H of B, B prime is H of B prime for all B, B prime in B. You just use this definition of H. That's all we'll say about this. And later on we'll use this theorem to get our isomorphism.